Now that you've had a chance to explore Cauchy sequences, we're going to explore the relationship between Cauchy sequences and convergent sequences. One of the things I would strongly recommend before watching this video is try working the problems for Cauchy sequences and convergence. At the very least, try to work out number 1 and number 2 from those activities. This video is going to assume that you've worked those out and you at least understand what those lemmas say. Okay, so as I mentioned, we're going to explore the relationship between Cauchy sequences and convergent sequences. We are going to review the definition of Cauchy sequences. We are going to prove that every convergent sequence is Cauchy. That proof is not going to be too bad. And then we're going to try to go the other way. And one of the things that we're going to have to do before we do that is introduce 2 monotone sequences that are associated with any bounded sequence. And then we're going to use those sequences to outline the proof that every Cauchy sequence is convergent. We're not going to do the whole thing. I'm going to leave you to fill in the details. Those are in the class activities. All right, so recall the following definition. A sequence xn is Cauchy if for every epsilon greater than 0, there exists some big N in the natural numbers such that whenever little m and little n is bigger than big N, we have xm minus xn, the absolute value of that, less than epsilon. So we'll go directly into our first theorem. Let xn be a convergent sequence. Then we're going to prove that xn is Cauchy. So we're going to start by letting epsilon greater than 0, and we're going to find some natural number big N such that every time little m and little n are bigger than big N, we have absolute value of xm minus xn less than epsilon. So we know that xn converges to some number L. That's going to be helpful to us. That means there exists some big N in the natural numbers such that every time little n is bigger than big N, we have absolute value of xn minus L less than, well, any positive number we want. It turns out that epsilon over 2 is going to be helpful. If that looks familiar, you're probably anticipating that there's going to be some kind of triangle inequality stuff going on, and that is absolutely true. So every time we have little m and little n bigger than big N, we're going to have absolute value of xm minus xn. Well, that's going to be equal to the absolute value of xm minus L plus L minus xn. We're just subtracting and adding L, not changing the quantity, but it's making things nicer to use our triangle inequality. That's going to be less than or equal to absolute value of xm minus L plus the absolute value of L minus xn. Notice that when we change the order of the subtraction, we get the same absolute value. We're going to do that in the second term to get absolute value of xm minus L plus absolute value of xn minus L. Note that little m and little n are both bigger than big N, so those two absolute values are each less than epsilon over 2. So we get epsilon over 2 plus epsilon over 2, which equals epsilon. And that gives us our proof. So that wasn't too bad. Now if we want to go the other way, we're going to start with letting xn be a Cauchy sequence, and we want to prove that xn is convergent. That's going to be a little bit tougher because we don't know what they converge to. That's going to be hard to use the definition. So how can we make that easier? Well, remember, we know that bounded monotone sequences always converge, even though we don't know what they converge to. So we're going to try to link xn, our Cauchy sequence, to some bounded monotone sequence. We're actually going to link it to 2 of them. Either one of those is going to be a good tool for proving that our Cauchy sequence converges. So first of all, we're going to define some sets. S1 is just the set of all the terms from the sequence. So starting x1, x2, x3. And this is literally a set now, not a sequence. Although when we talk about infimum and supremum, we're going to kind of use those interchangeably. S2, we're going to get the subsequence that you get from removing the first term. So we're going to start with x2, then x3, x4, etc. S3 is going to be the set you get from taking the subsequence from removing the first two terms. So we get x3, x4, x5, etc. And in general, Sn is going to be the set you get from xn, xn plus 1, xn plus 2, etc. So we're going to define two sequences related to this. A sub n is going to be the infimum of Sn, and B sub n is going to be the supremum of Sn. And note that both an and bn exist since the sequence is bounded. Sn consists of terms from the sequence, maybe not all of them, but since the entire sequence is bounded, that means all the Sns are bounded as well. And so bounded above and bounded below, so the infimum and supremum of all those sets exists. So that's nice, they're bounded. Question is, I want to know if an and bn are monotone. I want to know if they're bounded so that I know whether or not they converge. So what happens is, if m is less than n, we need to somehow know the relationship between am and an, and that's where one of the lemmas from the activities comes in. So this is one of the ones that I am assuming that you know. If you have a and b subsets of the real numbers, where a is a subset of b, well, let's see. We know that any upper bound of b is also going to be an upper bound of a. Since the supremum of b is an upper bound of b, that means it has to be greater than or equal to the supremum of a. Any lower bound of b also has to be a lower bound of a. Since the infimum of b is a lower bound of b, it has to be less than or equal to the infimum of a. So those are nice inequalities for us to have. And if we have m less than n, we can say something about the relationship between Sn and Sm. Now remember, n is the bigger subscript. That means it actually has fewer of the terms of the sequence, right? We take am through an minus 1, we remove those from Sm to get Sn. So that means if n is the bigger subscript, it is a subset of the s with the smaller subscript. So Sn is a subset of Sm. So from our lemma, we know that the infimum of Sm is less than or equal to the infimum of Sn, which means that a sub m is less than or equal to a sub n. And from the second part of that lemma, the supremum of Sm is greater than or equal to the supremum of Sn. That tells us that Bm is greater than or equal to Bn, which means that An is an increasing sequence, Bn is a decreasing sequence, so they're both monotone. All right, so we know they're monotone, but if they're not bounded, that doesn't do us any good in terms of figuring out if they're convergent. But we know that xn is Cauchy, therefore we know xn is bounded. That means we have a lower bound for the terms of of the sequence. We'll call that little m. We have an upper bound for the terms of the sequence. We'll call that big M. So little m is less than or equal to all the terms. Big M is greater than or equal to all the terms. So here's some observations. First of all, we know that A1 is the infimum of S1, right? Now, one of the things about the infimum of S1 is any lower bound of S1 has to be less than or equal to that infimum, so m is less than or equal to a1. We know that a1 is less than or equal to an for all n because an is an increasing sequence, right? That tells us that m is also less than or equal to an. We also know that the infimum of Sn is less than the supremum of Sn. That's kind of obvious. The lower bound has to be less than or equal to the upper bound. That tells us that An is less than or equal to Bn. And if we play the same games with B1 and Bn as we did for A1 in the first two bullet points, we get B1 being the supremum of S1 implies that any upper bound of S1 has to be at least as big as B1. So B1 is less than or equal to big M. Since Bn is less than or equal to B1 for all n, remember Bn is a decreasing sequence. That means that Bn is less than or equal to m. And then for all n, we get m is less than or equal to an, which is less than or equal to bn, which is less than or equal to big M. Which tells us all together in a really nice, concise way that both an and bn are not just bounded above or bounded below, they are just bounded. They are bounded both ways, above and below. So they are monotone, they are bounded. That means they are convergent, which means that an converges to some number a, bn converges to some number b, and these are very nice candidates for what our Cauchy sequence will converge to, right? So what do a and b have to do with xn? Well, we're hoping that xn converges to a, or if not, maybe to b. I don't know. We're gonna try something. We're gonna try it. All right. So it turns out it converges to both of them, right? So, which by the way means they're equal, right? But we're going to set up the proof that xn converges to a. I'm not going to fill in all the details. That's for you to do on the activities. But I'll set things up for you because it is rather meandering, all right? So here's what we want. Absolute value of xn minus a less than epsilon. We want to make it that be true as long as little n is sufficiently large, right? So we're going to be playing a lot of triangle inequality tricks, right? We'll do something like subtracting and adding the same thing to the inside of that, minus x and a plus s, kind of like we did for the first proof in this video, right? And then that's less than or equal to xn minus s plus absolute value of s minus a, right? That's just using the triangle inequality. But we can actually take that a step farther. We can take that actually many steps farther. If we subtract and add two numbers, right? Subtract s, add s, subtract t, add t. We can apply the triangle inequality twice to get that less than or equal to absolute value of xn minus s plus absolute value of s minus t plus absolute value of t minus a. And if I want to be honest, we can extend this as long as we need to split them up into as many terms as possible, as long as we can get each term to be arbitrarily small, right? Less than some epsilon. We can make that epsilon small enough so that they all add up to just one epsilon. It turns out we're only going to need to do this in 3 terms, but in principle we could go as far as we need to. All right, so remember, we want absolute value of xn minus a to be less than epsilon. And since we want to find a bunch of terms that are going to be arbitrarily small, we want to look for things, for quantities that we know, based upon our assumptions, that we can make arbitrarily small and positive. Remember, need to be positive, right? So first of all, we know xn is Cauchy. So we know there exists some n1 in the naturals, such that if little m and little n are bigger than that n1, absolute value of xn minus xm is less than, I'm going to call it epsilon 1 because it's probably not going to be epsilon. It's going to be epsilon over 2 or epsilon over 3 or epsilon or square root of epsilon. Who knows? Some kind of epsilon, some kind of small positive number, right? So absolute value of xn minus xm, we can make that small. So that's comforting. Remember, we also know that an converges to a, and so there's some, I don't know, we'll call it n2, such that when little n is bigger than n2, absolute value of an minus a is less than some other epsilon. Again, could be epsilon over 2, epsilon over 3, could be a lot of things, right? We'll figure that out later. Now, that's actually really nice, but it does leave a little gap in our triangle inequality, or triangle identity, right? So we have absolute value of xn minus a. We can get absolute value of xn minus xm, but then we've got to add an xm in there. And it's okay to have that an minus a, but then we got to subtract an an in there somewhere. So that little question mark kind of has to be absolute value of xm minus an. And the thing is, we don't have any choice over what n is. We do have a choice of what m is, right? We can make m whatever we want as long as we make m big enough to satisfy our Cauchy. So the question we might ask is it possible to find m such that absolute value of xm minus an is less than some epsilon 3? And the answer is yes. And this is a lemma that is in your in-class activities that I want you to work on. Again, I will get you started on it, but I want you to fill in the details. So if little n is a natural number, any natural number, then there exists some little m, a natural number, that is at least as big as n, such that the absolute value of xm minus an is less than epsilon. So how are we going to do this? Remember, we are going to make it so that little m is bigger than an. That might give you a hint of what it is. I don't know. So here's something to get you started. So first of all, remember that a sub n is the infimum of all the terms starting with xn and then after xn, right? Now, being an infimum means two things. One of the things it means is that it is a lower bound, and that means that an is less than or equal to xm, hint, hint, for all m greater than or equal to n. I see an m greater than or equal to n in there, right? First of all, that is true, right? But the second thing about being an infimum is that any number that is bigger than that infimum cannot be a lower bound. And if only I could figure out a number that is going to be bigger than an. Well, how about an plus epsilon, right? We know that an plus epsilon is not a lower bound for xn and all the terms after it. That means there is a term that is smaller than an plus epsilon. So put those three facts together to find your xm, and then put that together to make your triangle identity stronger. All right, so that's the way that we prove that xn converges to a. As I mentioned before, it also converges to b, and the way you will do that, maybe not surprising, is you're going to use the bn's. So a fun exercise for you after you show that xn converges to a, remember that bn is the supremum of Sn. We proved that bn converges to some number b. I encourage you to try proving that xn converges to b, and it's basically going to be the mirror image of the proof that you will do in proving that xn converges to a. And in fact, if you'd rather try to show that xn converges to b instead, I won't stop you. All right, so now you are ready to work on the activities for Cauchy sequences and convergence. Just go ahead and click the link below this video.